Welcome to this video. We're going to solve problem 5 from our notes. The velocity time graph below, velocity, represents the motion of a car on a city street. Use the graph to determine the acceleration of the car at this particular time, this moment, and this moment in time. Okay, how do I find the acceleration at 1.4 seconds? Well, what is acceleration on the graph? Oh yeah, I remember now. The slope is equal to the acceleration, because slope is change in your y-axis divided by change in your x-axis, and delta v over delta t, that is acceleration. So I need to find the slope at 1.4 seconds. You might think we have to go find 1.4 and trace up to the line and then trace over and get the exact y-coordinate and x-coordinate. Here's why we don't have to do it that way. Every single point on this line has the exact same slope. In fact, this straight line only has one value of slope. So there's only a single acceleration for this entire line, and that single value includes the acceleration at 1.4 seconds. How do I know there's only a single slope for this entire line? Because the line is straight. The steepness is not changing. The line isn't getting steeper, it's not curving to get shallower, so the rise over run is constant for any straight line. So there's only one acceleration, and I can then choose any 2 points that I find on this line. I'll choose these 2 points. You can either do y2 minus y1 over x2 minus x1, or you can do rise over run. So to get from the first point to the second, I have to rise 10 meters per second. So the rise is 10. It's positive because we go up. And I have to run to the right 5 seconds. And that gives positive 2 meters per second squared. Now I should express my answer with the correct number of sig figs. All of the x values have 3 sig figs. All of the y values have 3 sig figs. So my answer should have 3 sig figs as well. Let's try that again. At 6.8 seconds, moving on to B. Okay, so 6.8 is maybe somewhere around here. What do we notice? At this point, we are on a flat horizontal line. Remember, the entire line has one slope because it's straight, and that one slope tells us the acceleration. So what is the acceleration of a horizontal line? The answer is 0. If you were to try and do rise over run, this does not rise or fall. So there is 0 rise and thus 0 slope. On to part C. Find the acceleration at 11.6 seconds. So 10, 11.6. And then I trace over. Maybe it's slightly below 20. Hard to tell. Fortunately, I do not need the exact coordinate, because this entire line right here has only one slope or acceleration value. So at 11.6 seconds, to get the acceleration, all I need is the slope of this line. And so I can choose any 2 points, including the endpoints. The slope equals the acceleration. And so how much do I have to rise up? Well, I'm going from 10 to 40. So that's a rise of 30 meters per second. And then how far over do I have to run? I'm going from 10 to 15. That's a run of 5 seconds. So when I do rise over run, again, it's positive 30 because we're moving up the graph to get from the first point to the second point. And then we divide by the 5 seconds. And this comes to positive 6 meters per second squared. Finally, part D. Find the acceleration at 17.6 seconds. Okay, 15, 16, 17.6. Trace over. And again, fortunately, I don't have to figure out what this precise coordinate is. I can use the two endpoints on this straight line because the straight line has one value of slope. And that tells us the acceleration for all of these times from 15 all the way to 25 seconds. So what is that acceleration? This time I'll do y2 minus y1 over x2 minus x1. This bottom coordinate is 25 seconds, comma, 20 meters per second. And this first coordinate, this first point, is going to be an x value of 15, comma, a y value of 40. When I do my slope formula, I do y2, 20, minus y1, divided by x2, minus x1. Remember, the numerator is in meters per second, and the denominator is in seconds. And this is going to give me 20 divided by 5, except it's negative 20 up top. So that's negative 4 meters per second squared.